Professor Surya Ramana is currently working in the mathematics department at Harishchandra Research Institute in Allahabad. He did his PhD from Madras University, Tamil Nadu. In 2001, he was the recipient of the Best Thesis Award from IMSC Chennai. His research interests include analytic number theory, additive combinatorics, and more. Professor Raman will now speak on quotient and product sets or subsets of the positive integers.
Thank you to Professor Manisha Kulkarni and the other organizers and the institution for inviting me to lecture in this program. I have only very rarely lectured to people outside the core group, so I had to think of a topic which would illustrate in some way what I am doing and also not be too technical. So first let me tell you a general vague theme that I study, and then during the course of the talk I'll try to illustrate this thing with a specific problem and tell you a result that we obtained not very recently, but it's a part of something. It began something that I still continue, so I should like to explain it in this manner. Okay, so what is the theme that I study? Well, as the student who introduced me said very kindly, that I am interested in combinatorial and analytic number theory. So analytic number theory is the use of analysis in studying questions about numbers. It seems a little far-fetched sometimes that you can answer questions about the integers using analysis, using things that develop from calculus. Okay, but it's a well-developed branch of mathematics with a 200-year plus history, and I combine analytic tools and combinatorial tools to answer questions which come up in number theory. That's my area of interest. Now, here is a theme, a vague kind of statement, but something that has guided many of the problems I've considered recently. So let us consider the natural numbers, for example. If according to you the natural numbers start with 0, or according to me they do, according to you if they start with 1, then the natural numbers form a monoid with respect to multiplication. Namely, you can multiply natural numbers. If they include 0, then you can add natural numbers. So they are a very well structured set, 0, 1, 2, 3, even intuitively without saying what structure means. It's quite clear that the natural numbers are very well structured. And the natural numbers have many interesting properties. So for example, even very simple ones, but slightly more complicated ones, like every natural number is a sum of 4 squares of integers of natural numbers. This is a famous theorem of Lagrange, for example. And there are many other interesting results about natural numbers. Now the question is, if you have an interesting subset of the natural numbers, let us say the primes, the squares, the cubes, these are all the first few sets that you meet when you study even basic mathematics. So the primes, for example, we have very difficult questions about the primes, whether even numbers can be written, whether integers can be written as sums of primes, 3 primes, 2 primes, 5 primes, and so on. So there are many additive questions about primes, there are additive questions about squares, and so on. Now, one might go further and ask, okay, the squares, the primes, these have certain properties given by famous theorems. Now, what if I take arbitrary but large subsets of these structured sets? Do they still retain those properties? Okay, this is a question one can pose. So here, you are just thinking of arbitrary subsets of primes, which are qualified only by the fact that they are large. Now, what is the meaning of large? Okay, that I'll make clear in the specific context that we consider. There are various ways of measuring size. So, if you look even at an intuitive meaning of it. You just take something that is picked at random from the primes, except that it contains a number of primes. Then the question is, does it retain the property, does it retain still some property of the prime? Say for example, if you think that every odd integer is the sum of 3 primes, every sufficiently large one at least, you ask, if I pick a large subset of the primes, is it true that every integer can be expressed as a sum of elements from that subset? Okay, so just asking these questions about subsets which are characterized only by the fact that they have large size. Do they still retain structure? Okay, so this is a general theme under which you can have a large number of famous problems, not so famous problems, and some relatively simple problems. So the problem I have described in these slides is a simpler sort of problem, but it will illustrate to you the difficulties involved in questions like this. Okay, so that brings us to the title of the talk, which is Ratios and Products of Subsets of Natural Numbers. Okay, so what do I mean by ratios and products of subsets of natural numbers? So let us see. First, let me define the two notions. So suppose A and B are subsets of the natural numbers. Okay, then one writes A divided by B in this fashion for the set of rational numbers, which can be written as a ratio A by B, where A comes from A and B comes from B. Okay, so that is the notation A by B, and A cross B is the set of integers which are of the form A into B, where one of the two multiplands comes from A and the other from B. Okay, so this is the meaning of these notations which I will use throughout the lecture. Alright, so also we will use these double bars to denote the cardinality, which means the size, the number of elements of these sets when they are finite, and we will mostly consider finite sets. Otherwise, we will have other ways of measuring their size. Okay, so this is the number of elements of A by B and A cross B, and in general we will use these double bars to denote the size of any set. Right. So with these two notations introduced, let us take up a very classical exercise. If you have done a basic course in analytic number theory, which probably you may not have, okay, this is a fairly standard exercise in the subject. So if x is a real number greater than or equal to 1, and A is the set of integers between 1 and x, then what is the number of rational numbers which can be written as a ratio of two elements of A? Okay, that's a pretty simple question to ask. If you take the integers from 1 to x, then what is the number of rational numbers which can be written as a ratio of two elements of A? And the answer is curiously involves as x goes to infinity. So you should always think of this thing as with x as a large real number. Okay, one can have even more precise statements. Nevertheless, you should think of x as a large real number, and A is the set of integers from 1 to x. And then you ask this question: what is the size of the set of ratios A by A? Okay, and curiously enough, this involves a transcendental number here. You have 1 over pi square over 6, which comes from the sum of 1 by n square times x square. So it's not really all the possible pairs that are there. The number of pairs of integers from 1 to x is nearly x square, because they are nearly, the integral part of x integers from 1 to x. So they are integral part of x square pairs, but not all of them give different rational numbers. And in fact, the number of different rational numbers produced is 6 by pi square, which is less than 1, of x square. Okay, we'll first try to understand the solution of this exercise, and then I will explain the problem I want to consider. I consider later. Okay, which is along the theme that I mentioned. Namely, first I have a question that I can answer for a structured set, namely the set of integers from 1 to x. And next I'll pose the problem, the same problem for an arbitrary but large subset of 1 to x. Okay, and then things become harder, and I'll tell you how we solve that problem, which is the main result that I want to explain. Okay, and therefore you see, first you have a simple question where A is a very nicely structured set. It's an interval from 1 to x, the set of integers in the interval from 1 to x, and I ask how many ratios can I get if I take A by A. Okay, so yeah, so the crucial thing to consider when you do this exercise is for any integer d greater than or equal to 1, you consider this set, like I have written script mdx, to be the set of pairs ab, okay, set of natural numbers between 1 and x, whose GCD is, okay, this is the set we work with. So you consider the set of all pairs AB with GCD D. Now, what happens? What are the properties of this MDX? The crucial property of MDX, which is the reason why one might say we are interested in this, is for any D greater than or equal to 1, if you look at the all pairs AB with GCD of A and B fixed to be D, then this map that takes the pair AB to the rational number produced by the pair is an injective map. It's an injective map. Okay, it's a one-to-one map. Namely, two different pairs with the same GCD cannot produce the same rational number. Okay. Now, why is that true? It's a very simple fact. Nevertheless, I shall review it for you. You take AB in MDX, and therefore A can be written as R times D, B as S times D, where R and S are co-prime. Only then the GCD of A and B will be D. Right? Therefore, now suppose that you have A by B is equal to A prime by B prime. You have two ratios equal. That means you have RD by SD equal R prime D by S prime D, because the GCD of AB and A prime B is the same D, because both belong to MDX. Okay? That means you have this relation, but the D's cancel, and you have this equation where R prime is co-prime to S prime, R is co-prime to S. So if R is co-prime to S but divides the product, it must be R prime. And likewise, if S is co-prime, you see you get the other way around too. Therefore, these two numbers are equal, which means that these two pairs are equal, which means that A and B are equal. So the reason for considering these sets MDX is because you want to study the ratios that are produced, and you would like to take a subset on which this ratio map is actually injective, so that if you estimate the size of this set, you will be able to get a hold on the number of ratios that are produced. Good. So what's the next step in solving this exercise? The next step is to note that these sets MDX partition the set of all pairs, they form a partition of the set of all pairs A cross A. Okay, so you take the pairs A cross A, any pair will have some GCD and therefore will fall into some MDX, and no two MDX have an intersection because their intersection, by definition, because they are separated by their GCDs. Okay, therefore you have another relation. These relations that I have written in blue are the important ones. Okay, so that's a color code, and I think I have been consistent with through most of the slides. Nevertheless, there are some others that are written in black. I'll explain that later. Okay, so you have cardinality A square is the sum of the cardinalities of these MDX as D varies from 1 to infinity. Okay, that's another relation. Now these two relations, the fact that this map is injective, and the fact that you have this relation, they are valid whether or not A is an interval. You take any subset of the natural numbers and you can define the notion, instead of MDX you can say MDA. You can split that the pairs that come in A cross A based on GCD. They will form a disjoint partition, and the map that goes to, takes A by B to A comma B to A by B will be injective. And this is a fact that's independent of the fact that A has structure, namely that it's an interval. Okay. Now we will record some facts which depend on the fact that A is an interval. Okay. So far we have not yet used the fact that A is an interval in Z. Alright. Now you see that the solution to this problem crucially depends on the fact that the original question is posed not for an arbitrary subset of the integers from 1 to x, but for the entire interval 1 to x. Okay. So first observation is MDX is the same as M1 of x by d. M1 means the pairs that have GCD1, that are co-prime. Okay. MDX is the same as M1 of x by d. Why is that? You take a pair that has GCD d, so A is RD and B is SD, R and S are co-prime. Then since A is less than x and B is less than x, it means that R is between 1 and x by d. R is an integer, so it's greater than 1. It's greater than 1 less than x by d, and R and S are co-prime, which means that RS belongs to M1 x by d. You can just trace these steps backwards to get the other way around. You take an RS in this set, you multiply by d, and you will get one which has GCD exactly d. Okay? So MDX is the same as M1 of x by d. So that's the other key fact. But this depends on the fact that you are considering an interval, because you see the fact that this R is between 1 and x by d and therefore still belongs to the interval is possible because R is less than 1 and x by d. If your set were not an interval, how would you know that R belongs to it? So this is a conclusion that you can come to only because of the fact that you are working with an interval. Okay. So next, you have therefore the relations cardinality A square is the sum of all the MDXs, and MDX in fact is the same as M1 of x by d. So it's a function, it just depends on x by d. Hence you have actually here, I have missed cardinalities on this side. There should be cardinalities indicated there. So there should be the two lines which I have missed. Now, the fact of the matter is the set of ratios has the same cardinality as the set of pairs that are co-prime, and this again depends on the fact that you are working with the interval 1 to x. So what is the number of ratios that can be produced from the integers from 1 to x is the same as the number of pairs that you can get which are co-prime. Okay, so why is this? Indeed, if you have a ratio A by A, then 1 less than R less than X and 1 less than S less than X would follow, because R by S is a ratio that is produced from A. Okay, so after cancelling off the GCDs, R and S would still be less than X, and they would obviously satisfy this condition. Thus, R by R comma S, the pair belongs to M1 of X, and R by S belongs to M1 X, the fractions produced from M1 X. Therefore, the cardinality of the ratio set is equal to the cardinality of the ratio set of M1 X. It's clearly, this is a subset. The small argument here shows that this is in fact equal, and that is equal to M1X because this map, the map that sends AB to A by B is injective on M1. Okay? So the ratio set, the cardinality of the ratio set A by A is exactly the cardinality of M1X. is the same thing. So what we need to do is to find out M1x, that is the number of pairs A, B with A and B less than x and A and B co-prime. Okay. Now, how do we find that? Okay, so we write down the relation that we had. Cardinality x square, integral part of x square is the sum of the cardinalities of M1x. Why do you get the integral part of x? That's just the cardinality of A. It's the number of integers from 1 to x. And you have this relation. And what we have to find is M1x. Now, for every x greater than or equal to 1, this equality holds. Okay? And therefore, you have to find this function M1 of x. Now, when you have a function of real numbers, let's say f of x is given by the sum of d greater than or equal to 1 of g of x by d. Okay, when you have two functions related by such a relation, there is what is called the Mobius inversion formula, which tells you that you can invert this relation. If for every x, f of x is equal to the sum over d greater than or equal to 1 of f of x, g of x by d, then f and g form a Mobius pair, and you can write one in terms of the other. Okay, this is a well-known basic fact in analytic number theory or elementary number theory. So you apply what is called the Mobius inversion formula, and because of that relation, it tells you that the cardinality of M1x is exactly this. Okay, so that function that is there outside goes into the same sort of formula, and you will have to put coefficients which are given by the Mobius function. Okay, this mu d is minus 1 to the power of the number of prime divisors of d if d is square free. For the case of 1, it's empty, so it's mu of 1 is 1. Okay, so you have this well-known Mobius function which you use, and you extract a relation for M1 from that relation. All right. Now, from this, it actually follows that since M1 is, we have already seen, is the cardinality of A by A, it follows from this relation that A by A is behaves like 6 by pi square cardinality of A square or x square. It's the same thing because the cardinality of A is x essentially. Now, how do you deduce this from this? That's a simple step, mostly just elementary inequalities involved. I don't give too many details, but the basic idea is when you have a formula which says M1x, the cardinality of M1x is given by the right hand side, then in the right hand side what you have is the integral part of x by d square, and you just want to think that you can approximate this sum by removing the integral part and replacing it with just x by d. Okay? When you learn these things for the first time, at least for me, the difference between integral part of x by d and x by d doesn't seem like a big thing. But when you have when you have sums of such things, especially with coefficients which take a sign which randomly changes, this can play havoc, the difference between x by d and integral part of x by d. Nevertheless, in this particular situation, you can make an estimation of the error. You can estimate the error and see that it's small enough, and conclude that in fact the integral part of x by d square can be replaced with simply x by d square. Okay, and then you see you get here mu d by d square times x square in principle, and mu d by d square is a very well known sum. It is the reciprocal of this sum sigma 1 by d square, which is pi square over 6, and that gives you the 6 by pi square. Okay, so by this method we have solved this classical exercise and shown that the number of rational numbers that are produced by the integers from 1 to x, it varies as 6 over pi square x square. Okay, so 6 over pi square, I don't know, perhaps you can tell me up to several decimal places what is ratio, but if you take it as 6 by 10, then it is about 60%. Okay, so 60% of the number of pairs is in fact the number of rational numbers that is produced. Not all of them produce different rational numbers. Now we come to the theme I mentioned before. So here is the question. So what can be said about A by A when A is not necessarily an interval but only a large subset of this interval? Okay, this is a question. Is it still true that A by A is comparable to A, the cardinality of A square? We saw that for the interval, up this double inequality here means there is a constant which we don't care about, say 60%, 50%, some proportion of A square. Is this still true? That the number of rational numbers produced is still a proportion of the total number of pairs, or does it fall dramatically down? Can it fall down dramatically? This is a question. Okay, so to precisely formulate this, so the precise formulation should have appeared on the next page, but I moved off. So the precise formulation is x be a real number, y be a real number, a and b be subsets of the natural numbers between in 1 to x and 1 to y, and a and b be large in the sense that they contain a positive proportion of the integers from 1 to x and similarly from 1 to y. Then what is the number of rational numbers you can produce? Okay, this is the question. Now here the only restriction we have on A is the size. There is nothing about its structure. It's not an interval. It's just an arbitrarily picked set of a certain size. And then we ask this question. Okay, so this is what we proved, that in fact it is not true that the number of rational numbers is a positive proportion of the cardinality of the set square. Okay, there are in fact instances where it can fall dramatically down, the number of rational numbers produced. So for every epsilon positive, there is a C epsilon such that the number of rational numbers is alpha beta to the power 1 plus epsilon times xy. The crucial thing is it's not 1. If it were 1, you would get back the fact that cardinality AB, if you see here, what you get is alpha beta to the 1 plus epsilon xy is essentially alpha beta to the epsilon times cardinality AB. This alpha beta to the epsilon can bring down the number. Okay, so this is optimal in the sense that you cannot remove the epsilon totally. Okay, there is this result is not valid with epsilon equal to 0. So this was the answer given to this question. Now why did we consider this question at all? Okay, so here is the motivation for the question. Let A be a subset of the natural numbers. Okay, then it's upper asymptotic density. When you have infinite sets, measuring the cardinality doesn't make sense. But what you can do is take the cardinality up to x, meaning look at the number of elements in that set up to x, divide by x, and look at that ratio as x goes to infinity. Okay, so there are two possible limits you can define. One is limit supremum, the other is the limit infimum. So limit supremum is called the upper density of the set. Okay, so Ax is the number of elements, and then you take this ratio and take the lim sup. That's called the upper density of the set. Okay. Now here is a problem that was posed by the Hungarian mathematician Sarkozy, who has worked a lot in combinatorial number theory, even combinatorial number theory and discrete maths in general. So he has a paper where he lists several open problems in these topics, and one of them is this question. Suppose you take two infinite subsets of the natural numbers with upper densities alpha and beta. Then if alpha and beta are not zero, so you have infinite sets with non-zero upper densities, what is the best possible function? So his question was, can you say just based on the density that there are infinitely many pairs, infinitely many terms of the product set which are within a certain gap, which depends only on the density? So if you are given two subsets of density alpha and beta, can you assert that there are infinitely many consecutive terms in the product set which are within, say, 1 by alpha beta or so? Okay, so this is a question that Sarkozy posed, and this is a question that we could answer, essentially give an optimal answer using the solution to the problem I mentioned. So I want to tell you how is that. Let us just take a simple example. Suppose A is the set of multiples of an integer h. and B is the set of multiples of an integer k. Then the densities of these sets A and B are 1 by h and 1 by k. Why is that? Because up to x you will have 1 x by h number of elements of A, and you should divide that by x and let x go to infinity. X will cancel and you will get 1 by h. Okay, so the upper densities are 1 by h and 1 by k, and the gap between consecutive terms of the product set, the set of all products A, B, if you take an element of this and multiply with an element of this, it's divisible by hk. And if you have two different elements of this, both are multiples of hk, and therefore the difference is at least hk. So the gap is at least hk. And you see hk is 1 over the product of the densities of the sets. Okay? So if you want a function, if you want to assert that there are infinitely many consecutive terms with a certain gap, the best possible in some sense is 1 over the reciprocal of the just the reciprocal of the product of the density. And what we could show in the same thing is that in fact there are infinitely many consecutive terms of the product, the gap between which does not exceed essentially what you get from this simple example, with a fudge factor which is a C epsilon and an extra epsilon here. Okay, so one can settle the problem of Sarkozy essentially optimally. Now, how does one settle this problem of Sarkozy? Here is the very simple path from the problem we solved to the problem of Sarkozy. That is, if the upper densities of the sets are given as alpha and beta, that means the way they are distributed asymptotically is like there are alpha x elements and beta y elements for any x and y, not necessarily any x and y, because the lim sup means that there are infinitely many x's and y's such that essentially this happens. So what that means is that if there are infinitely many x and y's such that the number of elements in intervals like this are greater than alpha x and by 4 and beta y by 4. You take A and B to be these two finite sets and now apply the theorem on ratios. Yes, we have a question. No. Yeah. So you apply the theorem and you see that the number of ratios is alpha beta to the 1 plus epsilon xy. Okay, and the ratio set, because A and B are subsets of certain intervals, their ratios sit in this interval. So if there are this many ratios in an interval of that length, that means there are at least two ratios which are this much distance apart, okay, by pigeonhole. And if you just write down that fact, so A by B and A prime by B prime is less than 1 by alpha beta to 1 plus epsilon y square, and then note that B and B prime are at least y square, you see that A B prime, which is an element of the product set, differs from B A prime, which is another element of the product set, by at most 1 by alpha beta 1 plus epsilon. Okay? So you just see therefore that you have two terms in the product set which are at least this much apart, and since there are infinitely many x's and y's, you can produce infinitely many consecutive terms which are. So this solved essentially the problem posed by Sarkozy. Indeed, it turns out that, and I have not explained in my talk because of time limitations, it turns out that this problem of counting ratios has application to at least one problem which is of interest in computer science, which is about the periods of the discrete law. Now, unfortunately, I will not be able to explain the result. Nevertheless, this was one application, and the other one which I have only mentioned is another application to this study of ratios. Okay. Now, returning to the theorem, why is this epsilon greater than 0 necessary? Why is this theorem optimal? Can't you remove the epsilon from the picture? Now, here is the simple example which will tell you that in fact this epsilon is necessary. So you take any integer m and take P to be the set of primes, P to be a set of any 2m primes. So take an integer m and take any 2m primes. And for any I subset of this set of primes, let di be the notation for the integer that is produced by multiplying all the primes in that subset. Okay? So you have a set of primes, and for any subset, you just write di to mean the product of all primes in that subset. Now, let SP denote the set of all these di's where I varies over subsets of P of cardinality m. So, P itself is a set of cardinality 2m, and then you look at the subsets which have half the cardinality, to look at all subsets which have half the cardinality, multiply, find all integers which are products of the primes in these subsets, and that is called SP. Now, if you look at SP, the curious thing is its ratio set diminishes substantially with respect to the cardinality of the number of elements in the number of pairs you can form from it. So, cardinality SP square is the number of pairs you can form from it, but the number of ratios you can form is substantially less. As in, if you take any epsilon positive, you can choose m large enough so as to make this ratio less in cardinality than epsilon times SP square. Okay? So this is the reason why there are sets where these ratios can diminish considerably in number. They need not be a positive proportion of the number of pairs you can produce. Now, why is this true? Okay, here is the simple reasoning that lies behind it. The cardinality of SP, it's the number of subsets of size m in a set of size 2m. So it's 2m choose m. Now, if you look at di by dj, di is a product of primes, dj is a product of primes. All the common primes cancel off. So what you get is d of I minus j and d of j minus I, which are disjoint sets. And the number of disjoint subsets of P, which has cardinality 2m, is 3 to the 2m. I mean, a set, another set which is disjoint, and then the union complement. So you have 3 things, and then you have 3 to the 2m. So the number of ratios is less than 3 to the 2m. On the other hand, the cardinality of SP square is 2mcm square, which a famous inequality, basic inequality for 2mcm, tells you that this is greater than 4 to the 2m by 2m plus 1 square. So there the size is less than 3 to the 2m, here the size is greater than 4 to the 2m. So the ratio can be, I mean, therefore if you compare the two sizes, you can, one is much smaller than the other. If you choose them large enough, you can bring down the size as much as you want. Using this, one can construct, then one has to do a certain number of things, and one can actually produce subsets in 1 to x such that the cardinality is greater than alpha x, but then the cardinality of the ratios is less than epsilon times alpha square x, so the cardinality of a square. So you can show that there are subsets of the integers from 1 to x such that the number of ratios produced is much smaller than the cardinality of the number of pairs. Okay? So this explains why our result is essentially optimal. Fine. So returning again to the theorem, so I've told you first I gave you an example to a simple, relatively simple exercise to motivate what we prove. Then I gave you a theorem, okay, along the theme that I explained to you in the beginning, and then I explained to you why this theorem is optimal. Okay, essentially you can't improve it too much, and now I should tell you a few lines on how one can prove such a result. Okay, so once I do that, of course I am done with what I have to say, and I suppose we move on to the next lecture. Now, so here we are. How do we prove this theorem? We follow the pattern of the classical exercise. So you look at these sets M, A, B, okay? They are sets of all pairs such that the GCD is D. Now again the map is injective, as I mentioned to you, and the cardinality of the ratio set, because these maps are injective, the cardinality of the ratio set is at least as big as each of them, or the supremum of all of them. Okay, because each of them produces for you an injective map, so you can take the biggest one that you have to get. Also, of course, you have this these sets partition the set, so you have this. So what you want is a lower bound for the supremum based on the fact that the set partitions like this. Okay. Note that unlike in the case of the interval where we knew that MAB1 was the answer to our question, here we have no idea because these sets are arbitrary. They can consist of all even numbers. Then they will not be co-prime. You won't find a pair which is co-prime at all. So MAB1 could be zero, empty. See? Therefore, you don't know the D which contains a large number of multiples in these sets. That's really the problem. This D is unknown. Whereas in the case of an interval, you knew that D equal to 1 worked. So that let me skip this first bound. So let's say that just starting from the relation that we wrote, you can find a bound, a simple bound, which is of this form, alpha beta square xy, whereas the theorem says it's essentially alpha beta. So from square one has to come down all the way to 1. Okay. So how does one do that? You see, the point is, so let's look at this. You see that by a relatively simple method, one can get that the ratio alpha beta, the number of ratios is alpha beta square xy. This needs to be improved all the way to alpha beta to the power 1 plus epsilon. So to do this, we have a certain iterative strategy which plays out a certain dichotomy that appears in this subject quite often. Okay, so let me just be somewhat mysterious and leave it there. There is a certain dichotomy which plays out, and that allows you to build an iterative strategy. But the problem with this iterative strategy is you can improve your bound if you are willing to sacrifice the D for which MABD is large. Like what I am trying to say is you have various sets MABD, whereas an interval D equal to 1 is known to be the kind that gives the answer. Whereas in the arbitrary sets case, you have to sacrifice your knowledge of D to get a better bound. The less you know about D, the better your estimate is. So there is some sort of an uncertainty principle playing out there. And with the aid of this iterative procedure, what we prove is something like this. So if you get alpha beta to the power of delta, then you can improve that delta. So if you have a delta, then you can, this iterative strategy allows you to improve delta to this thing for any q greater than or equal to 1. Okay? The simplest argument tells you that delta equal to 2 works. So starting from delta equal to 2, you apply this iterative strategy. For any delta, you can improve the result to this. So you just keep doing these iterations and see where they stabilize, and it turns out that they stabilize for delta of this form for any q greater than 1. But then since this is valid for any q greater than 1, you let it go to infinity and you get delta is 1 plus epsilon. And that completes the proof theorem. So of course I have hidden a large number of details. Nevertheless, the basic sketch is that there is an iterative strategy for improving the simplest bound that you can get for arbitrary sets, and this iterative strategy involves sacrificing the knowledge of the D that works if you want to improve your bound. Okay, so with all that one gets the theorem, and that completes my talk. Thank you.
Professor Anand Lewis is currently an assistant professor at the Department of Computer Science and Automation, Indian Institute of Science, Bangalore. He did his B.Tech in Computer Science and Engineering from IIT Delhi and obtained his PhD in Algorithms, Combinatorics and Optimization from Georgia Tech, supervised by Professor Santosh Vempala. Later, he went on to work as a postdoctoral researcher in the Department of Computer Science at Princeton University. His research interests include algorithm, randomness, and many more. Professor Lewis will now speak on a survey of probabilistically checkable proofs.
Okay, thank you for the introduction. So I talk about these things called probabilistically checkable proofs. They are a very exciting field of study in the area of computational complexity theory. But before I get there, before I start describing what probabilistically checkable proofs are, so let me give you a very nice and very surprising application of these things. Okay, so firstly, what is computational complexity? So if you have any computational task, so in computational complexity, we study how many resources does it take to perform some computational task. So what are the resources like? The algorithm, the most important resource is how much time does the algorithm take. There can be other resources such as how much memory does the algorithm take. Or there can be other things like, well, nowadays you have multi-core processors, so you can also ask how many processors does your algorithm need. Right, so there are many such ways to measure the complexity of an algorithm. So for simplicity, we'll assume that you have only one processor in the stock, and let's say we don't care about the space, and we only try to look at how much time do these algorithms take. Okay? So we'll say that an algorithm is efficient if it runs in time, which is polynomial in the size of the instance, input instance. Okay? So P is the class of all such problems which have a polynomial time algorithm. And there's also this another class of problems known as NP. So which are the class of problems for which there is an algorithm to verify whether a given solution is correct. So it's a little different from B because we are not solving the problem, but if you are given a solution, in this class we want to ask, can you verify in polynomial time whether the solution is correct? And one of the biggest open questions in theoretical computer science is whether P is equal to NP. Many of you might say, obviously not, right? I mean, P is like algorithm, solving a problem, and P is like you're checking whether the solution is correct, so obviously it shouldn't be. But, well, that's what many people seem to think, but we don't really have a proof that P is not equal to NP. And this is one of the biggest open problems in theoretical computer science. And it's, one of the central areas of study. So let's look at one of the kind of fundamental problems in this P versus NP, which is known as the satisfiability problem. Okay. So you are given a Boolean formula. You want to check whether there exists an assignment which satisfies it. Okay. For simplicity, we'll assume that your Boolean formula has this sort of structure. So you have these kinds of, clauses. We call these things clauses, where you have an OR of 3 literals, and the whole formula would look like an AND of these clauses. Okay. And for simplicity, we'll assume that each clause has exactly 3 literals. Well, firstly, it's for simplicity, and secondly, it's without loss of generality. So you can reduce any problem in NP to such a form. And we want to ask the question, does there exist an assignment which satisfies this or not? Right, so in this case, you can easily verify that it does have an assignment which satisfies this. So if you set, say, x1 to be true, x2 to be true, and say x4 to be false, then clearly it satisfies that. Right, so in this case, so the general problem is you want to determine whether there is an assignment which satisfies this. There's an NP hard problem, there's an NP complete problem, and so if you believe that P is not equal to NP, then we don't have an algorithm to solve such a problem. So let's ask a slightly related question. So if you're given such a list of clauses, so can we find an assignment which satisfies as many clauses as possible? So note that if you have an algorithm to solve the second problem, you can solve the first problem. Right? So if you find an algorithm, if you have an algorithm which finds the assignment which satisfies as many clauses as possible, take that assignment and check whether it satisfies all the clauses or not. Right? So this problem is actually quite hard than the previous one. But again, because we sort of believe that P is not equal to NP, we don't really expect to be able to solve this problem. So what do we do? So we cannot just give up and say, okay, this is a hard problem, we're not going to solve this, let's go home. So what we try to do is we try to solve this approximately, in a very formal sense. Is that so we want to find an algorithm that runs in time that's polynomial, but it finds a solution which satisfies maybe not as many clauses as it's possible to, but it finds a solution which satisfies a reasonably large number of clauses. So to make this formal, so we'll say that an algorithm is an alpha approximation algorithm if it guarantees that it will output a solution which satisfies at least as many clauses as alpha times the optimal solution would satisfy. Right, so this is pretty weird at this point, right? Because firstly it's an NP-hard problem, so we don't even know how many clauses the optimal assignment would satisfy. So how can one possibly prove that there is some algorithm which will satisfy at least alpha times the number of clauses as the optimal clause? So in here, in this area of approximation algorithm, the trick is that you want to find suitable upper and lower bounds on this optimal value and try to reason it. So let me illustrate that in this case of SAT and see what we can do. So for SAT, we have a very trivial bound on the number of clauses. Where if you have m clauses, clearly the optimal solution is at most n. It's a kind of a trivial upper bound. Let's work with this and see how far we can push it. So if I can find an algorithm, if I can find an assignment which satisfies at least alpha fraction of all the clauses, then that will be an alpha approximation algorithm. Because m is at least the cost of the optimal solution. If you get a solution which satisfies alpha m, then you satisfy alpha times the optimal solution. So if I can find such an approximation algorithm, that would be an alpha approximation algorithm. Okay, so let's look at a trivial algorithm and see what it does. What value of alpha we can get for it. So here's a very trivial algorithm, which it's a randomized algorithm. So what I do is, suppose I have n literals, I'll go to each literal one by one, and let's say xi, I set it to true with probability half and false with probability half. So I do this independently for each literal. Okay, so it's a randomized algorithm. So, but for now, let's say that's okay. We'll see how to do it with the randomness later. Okay, so let's fix any of these clauses. Let's say xa or not xb or xc. So it doesn't matter which ones are negated, which ones are not. Let's just fix an arbitrary clause. Let's say it looks like this. And let's ask what is the probability that this clause is satisfied. So this clause would be satisfied if, say, xa were true, or xb were false, or xc were true. Okay, so that's not the only, so there are like many ways in which this can be satisfied. So if you want to bound the probability that the clause is satisfied, it actually turns out it's easier to bound the probability that it's not satisfied. So because it's an OR of three things, this clause will be false only if all of them are false. Right? So the probability that xa is false is half, the probability that negation xb is false is half, the probability that xc is false is half. So the probability that this clause is true is 1 minus half times half times half, which is 7 over 8. Right, so now we can see that it doesn't matter in this clause which literals are negated and which ones are not, right? Because you are independently assigning each literal to be true or false with probability half. Doesn't matter which ones are negated, which ones are not. The probability that the clause will be satisfied will be 7 over 8 in all these cases. Right, so okay, so then by linearity of expectation, any arbitrary clause, since it is satisfied with probability at least 7 over 8, you get that by linearity of expectation. The expected number of clauses is, you go over each clause and sum the probability that is satisfied. So that is 7 over 8 times the total number of clauses. And as we saw before, that is 7 over 8 times the optimal value. Okay. So therefore, this is a 7 over 8 approximation algorithm. Okay, so you might argue that it's a randomized algorithm. It might, in some cases, output something that's less than 7 over 8. But that's kind of a technicality. That's an easy way to get a deterministic algorithm which satisfies the same, which has the same 7 over 8 guarantee. But let's ignore those technical details for now. Let's just say it's a randomized algorithm. In expectation, it satisfies 7 over 8 fraction of the constraints. So it's a 7 over 8 fraction, 7 over 8 approximation algorithm. Okay. Good. So the very trivial algorithm, we already got 7 over 8. So can we do better? Can we get anything better than 7 over 8 for this? Turns out we cannot do better than this. It's NP hard to do better than this. What that means is, if you believe that P is not equal to NP, then this trivial algorithm of randomly assigning values to the literals, that is the best you can do. There is no better approximation algorithm. Okay, so another way to state it is that if you get something like an 8 over 9 approximation algorithm, that will prove that P is equal to NP. Right? So in that sense, this is the best that is possible. And how do we prove this is the best that is possible? Well, this is one of the applications of this beautiful theory of PCPs. It was a very beautiful theory. It was a big breakthrough when it was first proved, and it was first proved in like 1992. People have been studying it since then and still trying to understand the consequences that it has. Okay. So let's go ahead and see what these PCPs are. So the title says probabilistic checkable proof. So let's see what does it mean to check a proof. So suppose I claim that I have a theorem and I give you a proof. So what would be a proof? So I'll write down a bunch of mathematical steps. There's the first step, then the second step, which possibly uses the first step, and so on. And successively the ith step would maybe use all the things that you proved in the first I minus steps, and so on. And finally, in the last step, would be your conclusion, which is the theorem that you are claiming. Right? So given such a proof, it's kind of easy to verify that it is correct, right? Which means you just go over each step one by one, read it, see whether it does indeed follow from the previous steps, see whether everything is correct. Right? So in that sense, checking a proof is NP, as we mentioned earlier. So the question that we're trying to understand is, if you are given a proof, do you really have to read the entire proof to be convinced that the proof is correct, or can you ask the theorem prover to write down the proof in some special format and you just read a few random lines from the proof and you can check whether it's correct or not? If that were true, imagine how easy it would be to grade your exams, right? You just pick up check a random problem, random line, you'll be done. Okay, so the question is, can we do this or not? And that's kind of what we're trying to understand. So again, let's come back to the SAT example. So we had a 3-SAT formula. We want to see whether there is an assignment which satisfies this or not. Okay? So we'll say an instance is a yes instance if there exists an assignment which satisfies it. If there exists no assignment which satisfies it, we'll call it a no instance. So as we saw before, there is a yes instance. And as we said, because this problem belongs to NP, there is every problem in NP has a short proof that the problem is a yes instance. Okay? And what do we mean by verifying it? So if you want to be really formal, so the verifier is a Turing machine which has polynomial amount of memory, polynomial amount of time. The verifier should read this proof and verify that this formula is indeed satisfied. Okay? So what would a proof look like? So if you have a proof, you have to come up with some sort of an encoding scheme, right? Because the proof in mathematics will not be like a bunch of sentences. It will be a bunch of zeros and ones. Right? So for example, for this clause, for this formula, let's say the proof is 11101. So what does that mean? Well, so we kind of do the obvious encoding that the first bit here represents the value of x1, the second bit here represents the value of x2, and so on. Okay, so according to this proof, x1 you set to 1, x2 you set to 1, x3 you set to 1, x4 you set to 0, x5 you set to 1. So now if you have any verifier or a Turing machine, you can go and check that this assignment does indeed satisfy this clause. You go to the first clause, plug in these values, see that it's true. Then go to the next clause, plug in these values, see that it's true. Right, so any verifier you can check in polynomial time that this proof is indeed correct. And so we should point out that this is not the only proof for this formula. In general, NP problems in NP can have multiple proofs of correctness. Okay. Yeah, so like I mentioned, any Turing machine can verify in polynomial time that this is a correct proof. So let's be a little more formal about what the verifier does. Right? So the verifier reads the formula and performs some computation. So it reads the proof and the formula and performs some computation. Right? So let's say the verifier reads. So let's say f is a function that the verifier is kind of computing. Okay, so at this point I'm trying to be as abstract as possible so that you can kind of generalize this to all the problems. But for example, like we saw earlier, in the case of this Boolean formula, so what is the verifier going to do? It's literally going to just evaluate the Boolean formula. Right? So f of x1 in this case would be just the Boolean formula itself. Right, so the question is, does the verifier need to read the entire proof, or can the verifier read a small number of bits on the proof and make a decision? Right, so in general, I mean, it would seem like the answer should be no, right? Because if suppose f was only looking at one bit of the proof, right? Suppose f of x1, x2, x3 up to x6 was equal to x1, right? So then the prover can always set x1 to be 1 irrespective of whether the formula is satisfiable or not, set all the other bits to be anything, and the verifier will accept. So you have to be a little careful about these kinds of things, that the proof would not be an obvious proof. It would have to be encoded in some way so that these kinds of things cannot happen. Okay. Right. So in such case, we give the verifier an extra power. So the verifier is allowed to be randomized. Right. So random is a very, very powerful tool in computer science, which I feel is kind of not really emphasized enough. So like we saw this algorithm also, we're just assigning each xi to be +1, true or false randomly, and it turned out to be an optimal algorithm. It was pretty cool. Right? So here also we'll allow the verifier to be randomized, and we'll say that the verifier needn't always be correct, but it should be correct most of the time. Okay, so we'll kind of formalize what all these things mean. Okay, if you want to be really formal, so let's say there's a parameter r, so that the verifier can toss r random coins and make some decision based on that. Okay, so let q be the number of locations that the verifier is allowed to look at. Okay. And so these are what the verifiers can do. So what are the guarantees that we should have? Right, so if the SAT instance is satisfiable, then the verifier should accept with a large probability. Ideally it should be close to 1, but since we are being formal, let's say it should be at least C, some number C. So you should think of C as being something close to 1. Okay. And if the SAT instance is not satisfiable, the verifier should accept with some small probability, S. Okay. So ideally we should think of S being something very far from 1. Okay. Right, so ideally we would want C to be 1 and S to be 0. But that might not always be possible, so let's even relax what we want. Let's say C minus S should be some omega 1, some constant. That's all we want. Good. So that is the setup. That's what we want. So what can the verifier? So how does this game work? So the prover will write down a proof in certain pre-specified format. So the verifier will toss r independent random coins based on whether they came out to be heads or tails. The verifier will decide upon few locations to look at. So let's say the locations are L1, L2, L3, L2. You will go and read these locations of the proof, look at what values there are, and based on those you will compute some functions only on those locations. So instead of reading the whole proof, you will read these few locations of the proof. You will compute some function g. What g is, it will depend on the problem, depend on the protocol, depend on various other parameters. But let's say it computes some abstract function g. And what it does is, if this function g evaluates to 1, then the verifier accepts. If it evaluates to 0, then the verifier rejects. Okay. So this is the protocol, this is the setup that we are going to play with. And okay, so right, so what kind of problems have such a protocol? So let's say we denote by this PCP C, S, R, Q, which have all the languages which have a probabilistically checkable proof with these parameters. I mean, like all those languages which have a guarantee, like what I mentioned in the previous slide. So okay, so ideally we want Q to be order 1. Q should be some absolute constant, and we want R to be log n. So why do we want R to be log n? It's because so ideally the length of the proof should be polynomial in size of the instance. Right? So if you have polynomial size instance, since you are using randomness only to decide which locations to look at, using log n bits of randomness you can test the entire proof. Right? And since you are only needing q times a constant number of queries, so the total number of amount of randomness you should need is ideally some log n times q, which is order log. or another way to look at it is that if you enforce that R is ordered log n, then that sort of already implies that your proof suffices to be polynomial length, because you cannot look at a proof anything larger than that. Okay, good. So what kind of PCP, what kind of languages have such proofs? So in kind of a very surprising breakthrough result, we showed that it was shown that this class of languages, PCP C, S, with R equal to log n and Q equals to order 1, is exactly equal to NP. Okay. So this is kind of a huge result proven by, well, it was proved by this Arora, Lund, Motwani, Sudan and Sekedi, building upon the previous work of Arora and Safran. And more recently in 2004, Dino gave a completely different view of this theorem. So it's hard to overstate how awesome this theorem is. So typically, we define NP as those languages which have a polynomial length proof of their membership. Now here you're saying you can have a polynomial length proof, but you don't need to look at the entire proof. You only look at a very small subset, a very small random number of locations in that proof, constant number of locations in that proof, and you can decide whether a given string belongs to the language or not. Right? So it's kind of like giving a new definition to NP. And okay, so it's not just like a new definition to NP, it has lots of consequences. So using this kind of a theorem, we can even show that this 7/8 algorithm, approximation algorithm for 3-SAT is the optimal algorithm that you can get. Okay. Right, so this has lots, so I'll not have time to go into the proofs of this theorem. Proving this usually take like 1 semester, but since we only have like 10 more minutes, let's skip that. Okay, so let me try to give you a high-level outline of how you would use such a PCP theorem to prove that the 7/8 approximation algorithm is the best we can do. Okay, so another thing I should mention is that I've been deliberately vague about what C and S are here. All I said was that C should be close to 1 and S should be, smaller than 1. So it's because there is that's kind of all we need, that there should be a gap between C and S. There is a fair bit of room here to play with between there's a trade-off between if you can increase Q, you can decrease S and these kind of things. So there's a lot of room here to play with. So that's why I've been deliberately vague about what exactly C, S and Q are. Okay. Okay, so let's see how to use the existence of these kinds of PCPs to prove these kinds of optimality of approximation algorithm. Because these types of results are known as hardness of approximation. Because we got an approximation algorithm, we want to prove that it's NP hard to get a better approximation algorithm. Okay, so those kinds of results, we kind of refer to them as hardness of approximation results. So let's look at why a PCP implies any such hardness of approximation. So what did we do here? Right? So we tossed a bunch of random points. Right? So let capital R denote the string of heads or tails that we got. Okay? So based on this capital R that we got by tossing random points, we decided on Q locations. So let's call them L1R, L2R, LQR. We went to those locations, read whatever the bits there were, and evaluated some function G on those bits. Okay? So let's look at the multi-set of all such possible queries or tests that we can do. Right? So for each value of R that you get from here, you will get a bunch of locations, and for each such bunch of locations there is a test. Right? So let's look at this multi-set of tests. Okay? So this multi-set of tests can be viewed as a SAT problem in itself. Right? So why is that? So the prover is trying to convince the verifier that the SAT problem has a solution. So the prover wants to give a proof such that the verifier will accept it with high probability. Right? So the prover doesn't know what question the verifier is going to ask, because that is based on these random points. Right? But what the prover knows is that these are the multi-set of questions that the verifier could ask. Right? So the prover wants to write down a proof where the variables are these kinds of variables of the proof, and you want to maximize the probability that the test that the verifier asks passes. right? So since we are only kind of given the multi-set of tests, so what the prover wants to do is, the prover will view this as a set of constraints and try to find an assignment to these L1, L2, L3 such that as many fraction of these constraints that can be satisfied as possible. Okay. So the prover what the prover wants to do is solve this kind of a constraint satisfaction problem. So L1, L2, L3 are the variables. So these are the set of constraints. So the prover wants to find an assignment which satisfies as many constraints here as possible. Okay. And right. So that is what the game is. Good. So what can we say about this new constraint satisfaction problem for the prover? So what we know is that if the SAT instance is satisfiable, then the verifier accepts the property at least C. So what this means is that if the prover writes down the correct proof, then the verifier will pick one of the random constraints from here and check that. That will pass with probability at least C. So what that means is if you look at the multi-set of the constraints here, the correct assignment will satisfy at least a C fraction of these constraints. Okay. And likewise, if the SAT instance is not satisfiable, then the verifier accepts with probability at most C, no matter what proof the prover gives. So what that means is that any assignment to L1, L2, L3, L poly n will satisfy at most S fraction of these constraints. Right? So again, the reasoning is the same. So what the verifier does is it looks at this multi-set, picks out a random constraint from here and checks that. And because that protocol passes with probability S, so that means that at most S fraction of these constraints are satisfied under any assignment. Right? Right. So because we know that checking whether a SAT instance is satisfiable or not is NP hard. What this means is that if you look at this constraint satisfaction problem, determining whether there exists an assignment which satisfies at least C fraction of the constraints versus whether all assignments satisfy at most S fraction of the constraint is NP hard. Right? Because if you could distinguish between these two, then from the argument which I showed you in the previous slide, you could potentially solve the SAT problem. Since we know that that is NP hard, what this means is you cannot do this. Okay? So if you have a PCP, then if you look at these kinds of these kinds of constraints, determining whether it's an assignment which satisfies at least C fraction of these constraints, or whether all assignments satisfy at most S fraction of constraints is NP hard. Right? So this sentence itself gives you a hardness of approximation type result, right? So it says that if you look at these kinds of constraints based on G, you cannot have an approximation algorithm better than S divided by C. It's NP hard to do something better than S divided by C. Right? So it's a very nice, very simple idea, but a very powerful idea. Right? So let's look at this closely. So you want to determine whether you are in the case when there is at least when assignment satisfies at least C fraction of constraint, or is it the case that there exists all assignments satisfy at most S fraction of constraint. Right? So now suppose you had an S divided by C plus epsilon approximation algorithm. So what does that mean? So if you're in the first case and you use this approximation algorithm, you will satisfy at strictly greater than S fraction of the constraints. Okay. In the first case, if you can use this algorithm to satisfy something that is strictly greater than S fraction of the constraints. Whereas in the second case, you can satisfy at most S fraction of the constraints. Then no matter what algorithm you use, you will not satisfy more than S fraction of the constraints. Okay. So if you had an approximation algorithm between whose approximation guarantee was strictly greater than S divided by C, you can distinguish whether you are in the first case here or whether you are in the second case here. So whether you are in the first case or distinguishing between these two cases is NP hard. Therefore, you cannot get an approximation algorithm better than S divided by C for this G problem, assuming P not equals to NP. Okay. So if you want to prove that this 3-SAT problem cannot have a better than 7/8 approximation, so what do you have to do? Well, firstly, you have to come up with a G such that G of L1, L2, L3, all this looks like, like a this 3-sat formula, which should look like an OR of all these things. So what that means is firstly Q should be equal to 3 and G should be G of x, y, z should be x or y or z. Right? And S divided by C should be 7 over 8. Right? So this was breakthrough result proven by Hastad, who showed that you can indeed get something like this, thereby proving that this trivial algorithm that we had is the best we can do pretty much. Okay. So there have been like many other applications of PCPs, but given the amount of time that I have, I don't think I'll be able to go into any more details. So there are questions. Sure, yes. Constant sizing in the input instances. Okay.
Here, can you bring from this position in S1 and that position is given? What is it? For example,
so usually those kinds of things are not NP hard, because in NP hardness typically you look for as n tends to infinity. Usually for those kind of problems they might fall under PPAD kind of classes. I'm just guessing here, I don't know if it does or not, but yeah. Right, so typically for NP hardness you kind of look at the asymptotic case where n goes to infinity. So yeah, I'm not sure if PCP kind of machinery has been used for these kinds of constant size instances. So PCPs is about problems, right? Not about algorithms. It just says this problem is hard or this problem is easy. It doesn't say anything about a particular algorithm. Right, so I'm not sure if PCPs have been, people have tried to use PCPs in such an application. So people have mainly used these for hardness of approximation in these kinds of settings, or in distributed settings, or in other, or trying to prove complexity of other games, in interactive proofs and others. I'm not sure if people have tried to do these kinds of applications. Okay, I think I have very little time left, but no discussion on PCPs would be, I have lots of time for it. But no discussion on PCPs would be complete without saying something about unique games. So unique games is it's kind of very structured problem. So let me tell you what that problem is. So let's say your P is some large prime number. You are given a bunch of linear equations of this form. This really very fixed forms. Each equation has only two variables. x1 minus x2 is equal to some a1 mod p, x2 minus x3 some a2 mod p. You are given a huge list of such constraints, and the goal is you want to solve these linear equations, right? So you want to find values to x1, x2, x3 so that you satisfy these constraints. Okay, again you want to kind of find an assignment which satisfies the maximum possible fraction of these constraints. So what's good about these things is that if there exists an assignment which satisfies all of these constraints, then it's very easy to find, right? Why is that? So let's say there is there exists an assignment which satisfies all of these constraints. So let's say x1 is 0. So if x1 is 0 and you know that there exists an assignment which satisfies all of these constraints, then x2 has to be minus a1. There's no other option, right? Okay, so you fixed x2. Well, if you fixed x2 and you know there exists an assignment which satisfies all these constraints, then there is a unique value for x3 which will satisfy the second constraint. Right, same wise, if you go to the next one, you fix x1, there exists a unique value of x5 which will satisfy this constraint. Right, so this is kind of where the name unique games come from, that if you look at any constraint, you fix one of the variables, then there exists a unique variable for the other variable, unique value for the other variable which will satisfy this constraint. Okay, so therefore it's kind of easy in that sense that if there exists an assignment which satisfies all these constraints, you can find that assignment. So you should contrast this with the SAT problem, where even if there exists an assignment which satisfies all the constraints,
you cannot find it. It's NP hard to find such an assignment. Okay, so this is when the instance is completely satisfiable. So if I tell you that there exists an instance which satisfies at least 99% of the constraints, can you find this assignment? Right, so this previous algorithm which I mentioned, it doesn't work anymore, right? Because earlier you said that if you fix x1, then you uniquely get the value of x2. But here we don't know which 99% of these constraints are satisfiable. So you cannot use that algorithm anymore. Okay. Okay, so let's try the other things that we saw. Let's try to do a random assignment algorithm. Right, so our values are 0, 1, 2 up to p minus 1. So for each xi, we assign it a random value from this set. Okay. So in such a case, we'll satisfy 1 over p fraction of the constraints, right? So we'll kind of do the same analysis as before. So the probability that any constraint is satisfied is going to be 1 over p, right? Because let's say you assigned a uniformly random value to x2. Then x2 plus a1 is also uniformly random in this set 0 to 0, 1, p minus 1. So the probability that x1, again uniformly random from this, is equal to a fixed number is going to be 1 over p. And so again, as before, linearity of expectation, this assignment satisfies 1 over p fraction of constraints. And as before, you can kind of do away with the randomness and get a deterministic algorithm which does that. Right, but in this case, you can actually do slightly better than this. So there is this whole area of tools known as semi-definite programming. You can use those to get slightly better approximation algorithms, but still nowhere near solving, finding an optimal assignment. So in fact, we have no clue how to solve this problem. So this is, in fact, it was conjectured by Subhash Kot that you cannot really, this problem is like really hard, in that even if you are given an instance where you are told that there exists an assignment which satisfies 1 minus epsilon fraction of these constraints, it is NP hard to find an assignment which satisfies at least epsilon fraction of these constraints. Right? Another way to view it is that it's NP hard to distinguish between the two cases. First case is there exists an assignment which satisfies at least 1 minus epsilon fraction of the constraints. And the second case is that any assignment will satisfy at most epsilon fraction of constraints. Right, so this conjecture has, even though it's still open, it has had numerous implications in this hardness of approximation area for many problems such as the max cut or the minimum vertex cover problem. This gives the optimal hardness in the sense that the hardness that you get matches the best known approximation algorithm for these problems. So there are many other problems for which this happens, but let me not go into those details. And yeah, so this is kind of a very big open conjecture. So in fact, Subhash Kot got the Nevanlinna Prize in 2014, where one of the main reasons was for proposing this conjecture and studying its implications. Okay. And yeah, so like I mentioned, the conjecture is still open. So again, so there's a lot of things that you can talk about PCPs and unique games. Maybe I can spend many hours talking about these things, but I guess lunch is waiting for us, so I should try to wrap up soon. Right, so let me just say that these things are like a very central topic in the study of hardness of approximation. So while I mainly only talked about hardness of approximation, they have many other connections to topics in computational complexity theory, which I did not touch upon. And so there are many of these conjectures, like the unique games conjecture or the small set expansion hypothesis, which are all very closely related to these PCPs, but they are still open. And I feel that overall the power of randomness is in designing algorithms hasn't been fully understood, hasn't been fully exploited. You know, so like here we saw that a very trivial algorithm using randomness turned out to be optimal, and again we used randomness to prove that, even though NP is about the deterministic algorithm. So I think the power of randomness hasn't been very well understood. I think there's a lot more to be done here, and yes, I hope to see more results about these kind of things in the future. I guess that's all I have the time for. Yeah, thank you for listening.
Do you think is
the connection?
Well, so people generally, okay, this is, I'm just speculating here. So people sort of seem to believe that P is not equal to NP, but for the unique games conjecture, it's kind of, there is no such majority view, you know, like a lot of people think it should be true, a lot of people think it should not, it's false. Yeah, but, okay, so let me mention two more things. So there has been recent evidence both for and against the unique games conjecture. So in 2010 there was this paper which gave a sub-exponential time algorithm for solving the unique games problem. Right? So typically if you are given NP hard problems, you sort of believe that not only do they not have polynomial time algorithms, but they also shouldn't have sub-exponential time algorithms. Right? But for the unique games, there was a paper by Arora, Baraka and Stoyer in 2010 which gave a sub-exponential time algorithm to distinguish between those two cases. Right? So, okay, so it doesn't really disprove the unique games conjecture, but it sort of maybe seems to suggest that maybe it's not true. So that was maybe some slight evidence that the unique games conjecture might not be true. But more recently, very recently actually, like in 2018, there was a paper which proved that a very close cousin of the unique games conjecture is indeed true. So if you kind of, let me not get into details, let me just say there was something very closely related to the unique games conjecture was proven to be true this year. So yeah, so we kind of in the last decade we've had evidence both ways, but we are really nowhere near saying which way it should go. Yeah.
There are, especially in vertex cover and even possibly max cut, this theory does not address the existence of powerful heuristics which have solved very large problems. And is there any insight into why, for example, integer linear programs, which essentially are the canonical things, are solved regularly by these heuristic solvers on very, very large scale, DSPs especially? Does this theory have at least an indication of why it is? It's probably making some assumptions which problems posed in practice are not satisfying.
So it's not this theory which is making those assumptions, it's usually those heuristics which are making those assumptions that instances arising in practice have some sort of structure. Right? So, I mean, this kind of talks about the worst case complexity. So,
yeah, the question is worst case over an ensemble of all possible examples.
Right, so if an answer to why, or maybe a sort of an answer to why these heuristics work so well in practice is that usually the instances which arise in practice, they sort of have some structure which makes them easy. So there is this kind of area called this beyond worst case analysis of approximation algorithms, where they try to study these kinds of things, that if your instance has some special properties, can you get better approximation algorithms for these kinds of problems? And okay, so so it's not doesn't exactly answer your question that why heuristics work, but for example, in the case of unique games, if we know that the underlying instance satisfies some properties, then we can solve it in polynomial time. Or if it satisfies some other properties, we can, we know we can solve it in, depending on some properties, we can even solve it in polynomial time. And so maybe, so those kinds of approximation algorithms, you use these other techniques and the structure of the instance to provide some guarantees of the performance of the algorithm. And so I'm guessing somewhat implicitly or inherently, so these kind of heuristics are exploiting the structure in these instances which arise in practice. And maybe that's why they are working so well. Because for all these...
Any version of the theory which can generate, given a detail of a heuristic, can generate a problem which breaks the heuristic? Has anybody tried to do that?
You mean generate an instance?
Where the heuristic will not work. And for realistic heuristics, not...
Okay, for most of these realistic heuristics, people have manually constructed instances that say where these heuristics don't work well. But I don't think there is an automated theory of trying to come up with such instances. Yeah, maybe one could come up with some such thing. The worst example maybe could be posed as an optimization problem. Okay, I'm just speculating here. I haven't thought much about these things.